Alright, I want to look at symmetry right now. And remember, symmetry just means you take a graph, and if you do something to it, you reflect it or rotate it, the graph matches itself after you do that. That's what we mean by symmetry. And we're going to talk about three types of symmetry. First one being if you do a reflection of a graph across the y-axis and it matches itself. So remember that when you reflect a graph across the y-axis, what happens is that the x-coordinates change sign and the y-coordinate stays the same. So if you make that change and reflect the graph across the y-axis and the graph's the same as it was before, which means the equation is the same as it was before, it means that you have symmetry about the y-axis. And we call that an even relation. So the way you check for evenness, symmetry about the y-axis, if you replace x with negative x and the graph is the same as it was before, the equation is the same, you have symmetry about the y-axis. Symmetry about the x-axis, again, if you take any relation and you reflect across the x-axis, what happens is that the y-coordinate switches sign. Okay, x stays the same, y switches sign. So if you make that change and your graph is the same as it was before, which means your equation is the same as it was before, you have symmetry about the x-axis. And the third type of symmetry is when you do a reflection across the x and the y, or another way to say that is a rotation of 180 degrees. If you take your relation and rotate it 180 degrees about the origin, which is equivalent to doing reflections about both axes, both coordinates will switch sign. And if after doing that your graph matches itself, you have symmetry about the origin, which is what we call an odd relation. Alright, let's apply that to this situation. We have some unknown relation here, and so I'm going to check for the three types of symmetry. So first of all, is it even? Is it symmetric about the y-axis? If it is, replacing x with negative x will give us an equivalent equation. So making my substitutions, my replacements. Okay, so I say to myself, did I get the same equation after making the change as I had originally? Okay, no, I have something different. So it's not symmetric about y-axis. Okay, let's now do symmetry about the x-axis. Symmetric about the x-axis if when I replace y with negative y, my equation is the same as it was to start with. Making my substitutions. Negative y squared is y squared. Okay, is this statement the same as this statement? Okay, and again the answer is no. So this relation is not symmetric about the x-axis. Okay, testing for symmetry about the origin means that if I replace x with negative x and y with negative y, my relation would match its original self. So making the changes. So I have y squared times negative x okay, and so I say to myself, is this the same as this? Well, actually the answer is yes, because if I multiply both sides by negative 1, these are the same. Okay, so therefore the relation, you always want to end your proof with a statement as to what the answer is and why it is. So the relation is symmetric about the origin, which I can just use the word odd for that. The relation is odd because replacing x with negative x and y with negative y produces an equivalent equation. So there you go, testing for the three types of symmetry. Now, I just want to take this one step further, because often when we're dealing with relations, we're dealing with relations that are functions. And so I just want to give a sort of a simplified way of dealing with symmetry for functions. Okay, so when we're dealing with functions, we can use the notation f of x, which we cannot use if we're dealing with non-functions. So if you have a function f, and if you replace x with negative x, which is what the notation is saying here, you would produce equivalent y's. Okay, so replacing x with negative x produces y values that are the same. Okay, so you can test for symmetry about the y-axis, evenness, by doing this. Okay, which is exactly what we just did before. Just have a different notation for this. Okay. For symmetry about the origin, remember it would mean that if you replaced x with negative x as well as y with negative y, so replacing x with negative x, y with negative y, you should get the same function as you started with. Okay, so that's exactly what we talked about before, just a different notation. What I can do, though, is in this notation here, I can move the negative in front over to the other side. So an equivalent expression would be to say that f of negative x is negative f of x. And so you can think of oddness of a function to be, if you reflected the graph across the y-axis, you would get the equivalent graph if you had reflected it across the x-axis. Okay? And when we're dealing with functions, it's often convenient to use this form and this form of the symmetry test, because all you need to do is check for one thing. If you replace x with negative x and you get the same function, it's even. If you get the opposite of the original function, it's odd. I'll do an example of that in a second. You might be wondering about symmetry about the x-axis. Well, a function can't be symmetric about the x-axis. Think about that and you'll realize that's true. We've got a function here because we have f of x. One input for x produces one output, and we want to figure out whether this function is even or odd. Okay. Now what I often like to do if I've got time or the function's relatively straightforward looking is just take a value of x. So I'm just going to take 2, plug it in. I'm going to get 6, and then take the opposite value of x and see if I can get a feeling for whether this function is even or odd. So I have negative 8 plus 2, I have negative 6. So what I'm seeing here is that by replacing x with its opposite, I got the value of y, which is its opposite. And so to me, this is feeling as though the function is odd. Okay, but doing a numerical example does not prove that the entire function behaves this way. So what we need to do is we need to take an arbitrary value for x. And so let's take x equals a. So f of a we know would be a cubed minus a. If I took the opposite value for x, negative a, and replace that into the original relation up top, that's going to be negative a cubed plus a, and that can be written as negative a cubed minus a. And the reason I wrote it like that is because I have shown that f of negative a is equal to the negative of, what's this piece right here? It's this, it's f of a. Okay, see what I've done? I've shown that f of negative a is equal to negative f of a. And that's how you show oddness of a function. So let's make our statement. Therefore, f is odd because f of negative a equals negative f of a.